テルハ大鶴橋です。ユネスコパーク。
Ion collider physics, and what they did was they took two heavy nuclei, two gold nuclei, and bashed them at each other as fast as hard as they could. And what you get is a quark gluon plasma. So this is the stuff at the very beginning of our universe. And so this is where we all came from. And the big surprise that they reported was the quark gluon plasma was a liquid. And the reason that it was a liquid that they could tell was that as this liquid expanded, if there was a thin slot, it expanded in the directions perpendicular to that slot. That was the fastest direction. So go in this direction, and this is
すみません。うわ、怖っ。ああ、テルハ大吊橋。ああ。
So let's see how this job works. I think that's rather beautiful, and I'd love to see it again. So let's see it again. So it's coming down. As soon as it hits, it grows that corona, and that corona then breaks apart and splashes in all these different directions. And so the question is, well, what causes the splash? And so, we've talked about, and so it can be how big cell.
あ、ロックがある、ロック。
Other things I told you about, like the surface tension holding in easy this fluid flows. And then, of course, I need to know about what what is the surface? Is it a hard surface, soft surface, wet surface, dry surface, smooth or rough? These are the only things that matter. And after that, I've told you everything that you need to know. Notice I didn't say anything about the air around us because, that doesn't matter. I mean, I don't even feel the air, really. And the last time you felt the air were worried about the air in the room was when you were running up a flight of stairs and were gasping for oxygen, not because you felt the air in your face. But you do know that if you stick your hand outside the window of a moving car, you feel drag on your hand, and so it gets pulled back. So what we would think is that all these little drops that are moving out there are feeling drag because of the air there. So if we took the air away, we could get a really big splash. So this is the idea. So we want to show a truly high-class splash. And so I'm going to show you this movie again. And so this is the third time you've seen it. So get it into your mind. So this is an ordinary splash. Hits, forms a corona, and the corona breaks apart, and that's where the splash comes from. And now I'm going to do exactly the same experiment. So it's the same drops of alcohol from the same height, same size, same microscope slides. The only thing is that we put in a container that we could take some of the air out. So this is 1/3 atmospheric pressure. So this is the pressure that you would have gotten if you were at the top of Mount Everest. So you could live in here. You wouldn't be happy, but you could live there. Okay, so now let's see the very big splash that takes place.
片道中。
So here it
往復
comes,
30分
big
だって。
splash.
山の神。行かねえよ。
So, in the words of Ayarabi,
Yeah,
who
book
ordered
it,
that?
good.
Right? I mean, this is the thing, is that this was not supposed to
Book
happen.
it.
And so, after this, we were on the floor laughing hysterically
Oh,
for
good.
about a month. And
Book
before we
nice.
said, well, I guess we better start doing some experiments to try and understand something about this. But, those experiments are still going on today, so this is not particularly an easy nut to crack. But what I wanted to show was a few other movies of this. So this is now the same experiment, but now all we've done is we have a higher viscosity fluid instead of the water. So it's 10 times the viscosity of the alcohol. So it's the same thing, the same drop size, basically, from the same height. And so we want to see whether this would splash. And so this is an atmospheric pressure of 20 kilopascal. So that's just what we're feeling now. So I let this thing go. And I stop it here because it's clearly not going to splash, right? It's just spreading out smoothly, right? Okay, so let's just finish this movie.
Oh.
And okay, I lied to you again. But I'm telling you these things because these are not necessarily, I mean, okay, I've seen this before, but this is what we expected when we first saw it. This is not, I mean, so I'm trying to put you in our frame of mind when we first saw this. So this thing does splash, but it splashes with a very different shape and morphology than the lower viscosity one. And you can ask, does air matter there? And so we do this thing in reduced pressure, and air still matters. That is, if I take the air away, it stops splashing. So this is a very robust effect. So that what this is saying is you will not get splashing on the moon. You might get it on Mars, but not on the moon, because there's no atmosphere in that. Everyone asks that, but you know what high pressure is? It's another word for that is bomb. And so we try to avoid bombs in our lab, and we do that if there was a reason to do it, but we haven't done that particularly. Okay, so I'm ending up. I just want to show this one last thing. So there's lots of studies you can do with this. And so one of the questions that comes into this is, where does the air matter? And so beneath the drop, is the air mattering there? Is it mattering somewhere else? What I want to show you is looking at what's happening above the drop. So is the air mattering as the drop is spreading above this drop? And so what I'm showing you now is a photography called clearance photography, and this is helping you see the contrast between different index of refraction of the air at different places. And so I'm going to show you just a little bit of this. So I stop it here so you can see what I want you to look at. The drop is this big black thing, that's kind of uninteresting. That's not what I want you to see in these pictures. This black thing is a substrate. That's not what I want you to look at. What I want you to look at is, you can see something about the wake of this behind. And that's what this kind of photography is helping you pull out from the, that you couldn't easily see with your eyes. Okay, and so now let's see this whole movie go. Now I'm not going to stop it, and you'll see the whole thing. So if there's anything that maybe you can take away from this lecture is that when you go home tonight and you have a leaking faucet in your bathroom that's keeping you up at night, you can at least think that every time you hear that drop pop, something really beautiful is happening, and that shouldn't bother you so much. Okay, so this is one takeaway message. And so this is where I want to conclude, so I just want to end up with all of this. And so, I've been talking about the emergence of structure and various things, all having to do with fluids of one kind or another. And it's nature's texture. It's what really gives the texture of our world. And so I think that's something that I'm fascinated with. What gives it the flavor, the texture of what we deal with every day. And so I think it helps give appreciation to the world around us. I hope that each one of these things has been a surprise to you. It was certainly a surprise to us when we came across it. The other thing I want to emphasize is that there have been connections throughout for all the science. So the things that we could do on the tabletop had things having to do with biology, it had to do with memory, it had to do with the quark gluon plasma. All of these things are in different realms of physics, but we could learn something deep about them by these experiments that we do right here. And so what this is kind of showing you, these are some of the images, but nature reuses the same ideas in different phenomena. And that's the point of this.